go to the next speaker now. And now we are even deeper digging into the new research. Björn Palm from the Royal Institute of Technology. Please give us an overview now over the latest research and the coming research. You have the...
Thank you, Eva. Yes, so just to introduce myself a little bit more, I come from the Royal Institute of Technology, as you can see, and from a division called Applied Thermodynamics and Refrigeration. And we've been working with heat pumping technologies for 100 years. And you could say that this started with an invention, actually, at KTH, where two young students invented a refrigerator without any moving parts. And this was, you could say, the start of the company Electrolux. And Electrolux were so happy about this, so they sponsored a position at our university. So since then, we've been working with heat pumping technologies. Of course, up until the 1970s or beginning of the 80s, it was mainly about cooling, but since then we have been working more and more on heat pumps rather than refrigeration. So I'll start with the very beginning here. This is actually the original heat pump, the patent which was claimed back in 1834. Actually, they claim that the invention was a little bit older, so someone else, not this guy, Perkins, had the idea about this heat pump about 20 years earlier, but Perkins was the one who really made it. And if you look at it, you can see that there are basically four parts. To the right, there is a sort of a pot, a heat exchanger, where you can create ice. And to the left, you have another heat exchanger where you can cool, and you have a compressor and a valve in the center. So all of this is more or less exactly the same as a modern heat pump. So there is nothing basically which has happened since in the beginning of the 1830s, 200 years ago. So the question is, what more do we need to know? And of course, we have had one problem all since, well, at least the last 100 years, the refrigerants. 100 years ago, the homes were electrified. It was not electrification of the heating sector, it was electrification of the homes at that time. And people started getting refrigerators into their home, and the refrigerants at that time were, could be hydrocarbons, but also SO2 or ethers or ammonia or other chemicals which were flammable or had a strong smell or were poisonous. And of course, the manufacturers of the refrigerators, they wanted to sell, and they couldn't sell if they didn't have a good refrigerant. So that was the background, and I think Martin mentioned this before. So these guys, Midgley and Henny, they were given the task to develop a new refrigerant. And they did this and presented in 1930 the new refrigerant chlorofluorocarbon, CFC. And at the picture you can see how they demonstrate this by inhaling the gas and then blowing the gas over a candle, and the candle goes out. So that was the start, the beginning of the CFC era, or more well known as the Freons. Then it took 40 years, and then Midgley and Melinda found out that they were not so good, these CFCs. So we had to change to HFCs. We took out the chlorine, because the chlorine is what affects the ozone layer. But another 20 years later or so, we had the problem with the global warming. And the solution then offered by the chemical companies was to change to HFO. O stands for olefin, which means that the molecule has a double bond. So these molecules are not stable in the atmosphere. They thereby decompose, and they don't create a threat to the global warming. But now, just recently, we have learned that PFAS is also a threat to the environment. And both the HFCs and the HFOs belong to PFAS, with possibly one exception. Or two, or a few. And now the chemical companies are actually not offering any new substances instead of the ones we used before. And there has been several investigations about this during the last 30, 40 years, how to find new refrigerants. There has been projects scanning over 60,000 chemicals to try to find something which can be used as a refrigerant in the future, and some of the criteria is, of course, it should not be poisonous, preferably not flammable, and it should not be dangerous in any other way to the environment. And but still we haven't found anything, and I don't think anyone in the, how should I say, in the community really believes that there will be some new refrigerant coming up in the future. So the conclusion is that the synthetic refrigerants are on their way out. And I think the industry has already realized this. You could see this at the last fairs, that there are a lot of products with propane and other hydrocarbons. So this is one thing which is related also to the research of the future. The natural fluids are coming back, hydrocarbons, propane, isobutane possibly, and it could be ethers, it could be propane. There are several other possible candidates among the hydrocarbons. But there is also carbon dioxide, which has been used successfully for certain applications since 30 years or so in Northern Europe. And we have ammonia, which is used already for large plants, but could perhaps in the future also be used in smaller plants. And this is a research area, I would say. And if we look a bit further into the future, we could also imagine using water or air as refrigerants for certain applications. So what is the problem then if we go to this natural refrigerants? Well, the problem was 100 years ago, one of the problems was the flammability, and we still have that problem. We actually did a change already when it comes to the refrigerators, and that was some 30 years ago or so, when we changed from CFC refrigerants or HFC refrigerants to isobutane, basically, in Europe. And this transition was done in a period of about 5 years. And first the industry said, no, this is not possible, we cannot do it, it will be very, we will blow up people basically when we have a leak inside the refrigerator and someone sticks their head in with a cigarette in the mouth or something like that. But the industry worked on this, hard on this for a relatively short period of time, I would say. And by, for example, removing the possible ignition sources inside the refrigerators, removing joints, reduce the charge, and doing some other adjustments of the designs. I think we can see now that the designs are really safe. It is very, very seldom we hear about any accidents with refrigerators because of the refrigerant inside, the flammable refrigerant. But of course, if we want to use it in heat pumps, the charges will be larger. And one research area which we have been working on for some 10 years or so, but which is, I think we at our university were quite alone on working on, and that is to reduce the charge of refrigerant. So on the two pictures here, you see two prototypes of parts of heat exchangers, and with very small, narrow channels inside, which helps to reduce the charge. And we have demonstrated already that it's possible to run a single-family heat pump with about 8 kilowatt capacity with only 120 grams of propane. And of course, that would be much safer than having the similar charges originally in the original design. Industry is also working on this, we know that. You can see different models of plates for plate heat exchangers here. And you can see that the charge has been reduced about half by decreasing the pressing depth of the plates in this case. There could also be interesting things done with the compressors. Sorry. So to the left you see an ordinary hermetic compressor. The charge of propane inside the compressor would be about 70 grams. A lot of it is in the oil, and there's a big oil sump with 2 to 3 liters of oil perhaps, which absorbs a lot of propane. We could go to the type of compressors which has been used in electric cars, and then the charge would be perhaps 15 grams instead. This is, of course, we need to develop these compressors which are now in electric cars because they are not designed to be used for 20 years or so. But there's nothing fundamental we need to do it. We just need to make sure that they can last long enough. So that was one area which I see, reduction of charge. There are also several other areas which I think could be of interest. Martin showed a similar map of Stockholm. This is zooming out a little bit compared to Martin's map, but as in both cases, the squares here represent boreholes. And of course, you could imagine if you have so many boreholes in one area, that they could start influencing each other. So this is something we need to keep track of and understand how to solve. There is a recommendation in Stockholm not to have more than 20 or 25 meters, or less than 20 to 25 meters in between.
We have some disturbances.
The distance in between the boreholes should be 20 to 25 meters or so. And if the lots are small, this is not possible. But of course, most things which are a problem could also be a possibility. So if we use the boreholes during the summertime, if we recharge the boreholes during the summertime, we would actually heat up the ground. That could be one possibility, at least to eliminate the problem of the decrease in the temperature of the ground. So understanding the heat transfer in the ground and how boreholes interact, that is a research area which I think will continue to be of interest in the future. Another area is, what do we do with these apartments in the cities? I guess this is not what we want to see in the future, right? And so if we throw out the gas boilers, we need and replace them with heat pumps. What type of heat pumps would that be? How should they be designed? How should we supply them with heat from the cold side? Where should they get the heat from, so to say? Should we have sort of cold district heating, or should we have a local heat supply on the roof or in the basement, or what should we do? There is research needed here. Yeah, I talked about the possibility of a cold loop, and this has already been implemented, at least as a trial. And this is one example from Switzerland, and there are others as well. And as you can see, the loop is connected to boreholes in the ground, so the boreholes keep the temperature reasonably stable around the year. And during the summer, the loop is used for cooling, and during the winter, it's used as a heat source for heating. So this type of solutions is possible, and we will hear more about a similar solution in the last presentation today. Yes, what else? Yeah, I mean, so far we have talked about heat pumps as it was only to be applied for buildings. But of course, we can use heat pumps also for industrial purposes. And we could, is time running out? Or okay, yeah, okay, a couple of minutes more. So this is just an example where we see a heat pump for drying of timber. That could be one possibility. Nowadays, the pulp and paper industries have so much spare or waste wooden material, so they don't use heat pumps. But in the future, perhaps the value, the waste could be higher, and thereby could be good to use heat pumps. Yes, and we also could imagine industrial heat pumps for high temperatures. And this graph shows that there are already products available where we could produce temperatures up to perhaps 150 degrees. And more research is needed in this area to how to design these heat pumps, what type of compressors, what type of refrigerants, what type of oils should we use. So that is an interesting area. And then we have the district heating systems. Here in Stockholm, we have one of the world's largest district heat pumps in district heating systems, and several such installations. But one worry for the companies is how should we run this in the future if we have no HFCs or HFOs or CFCs to put in? Can we charge them with flammable refrigerants? Can we do that in a safe way? And I think this is a critical question for the use of large-scale heat pumps in the future. We can also use heat pump, see them as a part of the energy system and try to use them for reducing peaks in the electricity demand, switch them off and on, allow the electricity provider to decide when the heat pump should be running. We could introduce storage and combine that with heat pumps. We do that already. It could be done in a more elaborate way. One example is shown in the picture. And finally, of course, there are alternative cycles, a long list of alternative cycles. We are so far assuming that the vapor compression cycle is what we will use. But when it comes to research, we should at least investigate other alternatives. Some of these are available already, but cannot compete on the market, so to say. Some are still under development. But in my opinion, there is none of the other cycles which can compete with vapor compression in the next 10 years. Or I was hesitant whether to write 10 or 20 or 50 years here, because you need really good enhancement of the materials you use, for example, for electrocaloric or magnetocaloric processes to have them compete with the simple vapor compression cycle. So my last slide. The heat pump, it's an old invention, but there is still need for research and development to boost the electrification of the heating system. Thank you.
Thank you, Björn. Please take a seat. It's always rewarding to invite a researcher, because you get all those, things we don't really know yet. But we